So it has been 2 weeks, okay? I hope you are all good. So previously, we did the following, and we will change the subject today, basically, yeah? Let me just summarize what you should have learned, the key point what you should have learned till now, and then we will change to something else. So we did planes, right? So we did something with the points in the plane, and we said we can interpret the thing as either the Euclidean plane or the projective plane, right? And we can do all sorts of geometry in this R2 and just pretend we don't know about Euclidean or projective, right? And then the idea is we can prove theorems, and then they can be both. And later on, we can see whether the nature of the theorem is either Euclidean or projective, or even something else, okay? And if it's Euclidean, we had angles and length, right? And they were given by a scalar product, right? That's something we had. And for that, for angles at least on length, what we need is somehow a zero vector. And with respect to these directions, we can talk about angles on length. And these 3 points would give rise to a triangle. So this thing, or if I write it this way, it would be just the norm or the length of x times the length of y times cosine of the angle. Okay, so this is what we have done this time, like elementary geometry, so that we can move further. And today we want to do curves. So maybe the first step,
so is that classical differential geometry?
if you wanted to call it that way, yes. We have 2 types of curves. Either we have a smooth curve, right? Or we can have discrete curves. Okay? So what is a curve for you? Draw one.
Okay.
And then tell me what is important about such a thing. Okay, that's a curve. Very good. We have a bunny here. And what else? Draw another curve.
Draw another curve.
Which is different from this one.
Okay.
Okay.
Oh.
And another one?
Please.
Yeah, you can also do that. Let me do this. And what else?
So.
One class is still missing. What do you think it is?
One class. Okay. Like this.
That's just 2 curves, yeah? Or you can consider that 2 curves. But what is missing from here to here to here?
Oh, okay.
What is missing? What could be another class of curves? What is different? Can I?
Okay.
For example. So this one is closed, okay? And assume that you cannot really see the beginning and the end. It's something like that. And maybe this one is also a smooth plane, yeah? Everything is smooth, right? Here we will have one singularity in a sense. Okay? And here we have a not closed curve. But then we can also, a curve would be also something like this. And then you can self-intersection. And it can be closed or not closed, right? Okay. So these are the curves. And as you already see, we draw them, right?
Yeah.
We are not interested necessarily in what the equations for those are, right? So what are, I mean, it's kind of difficult to write down such an equation, I would say. Okay, so first, maybe, what properties do we want? Of course, we can always write, so curves are normally C for curve, or gamma for C, right? And it's defined on some interval, AB, 0, L. Well, L normally would be the length of the curve, right? Well, it can do Rn, but let's just do R2, right? Okay. Now, it's normally just a map like this, and we are interested just in the image of our curve, and not in the actual map. So when you have a map gamma of t and a map gamma of 2t, it would be the image would be the same curve. The only difference is that the interval is slightly smaller, right? So geometrically, it doesn't make any difference, right? So let me draw a slightly different picture so that I have more space to tell you what this is about. So we have here an interval AB. We have here interval CD. And we have, because it's easier, let's start with an open curve. Okay? So this is gamma. And let's consider this point here to be gamma of A. And this here, gamma of B. Perfect. Now, I can also map from C to D to this curve, gamma tilde. So what is this point here? Well, it could be gamma tilde C, or it could be actually gamma tilde of D, right? I mean, and then the other point would be the other one, right? So what is the difference, though, between the blue one, if I start with gamma tilde C?
The orientation. The orientation of it. Orientation.
Yes, you're right, right? So the red curve goes from here to there, while the blue curve can go both, right? Either this way or this way. So now, what is the difference between gamma tilde and gamma?
The image is the same, but the definition
are the same and the maps are not same.
Exactly. But so basically what we have is a map from this interval here to this one. We can call it phi.
Okay.
Right? Yeah. So what is the property of phi?
1 to 1.
So phi should be 1 to 1. No, phi should be surjective.
You said 1 to 1? Yeah? What else? What is the difference between this case and this case?
The orientation, or phi A,
what
B, or phi B, like that.
So in the first case, if the same orientation, I have phi of A is C, and phi, in the next case, we have phi of A would be D. What is the difference between these two cases?
So just like this phi maps A to D, so the interval is like this.
Yes. So the question is whether we do this and this way, or would we do straight ahead down, right? But what is the difference as a map from R to R? So if you would do, here's IB, and here is C and D, how would phi look like in that diagram?
Maybe like this. So the first case maybe if A maps to C, then it's like
Mm-hmm.
and another case like let me do like this.
Okay. Yes. So the difference is because you need that it's 1 to 1.
Yeah.
And surjective, so this interval must be mapping to this one. Yeah. So you have either it's always growing or it's always falling.
Yeah.
Okay, so if it's differentiable, the first case would correspond to the case where phi prime is bigger than 0, phi prime is smaller than 0. Okay, that would automatically give it's also injective, 1 to 1. Okay, so this case is called orientation preserving, and this one is called orientation reversing. So it's a this thing is called reparametrization. And either is orientation preserving or orientation reversing. Okay? Yeah? You had that before? Heard about this, something like this before? So now, this is an open curve. Let's do closed curves. How do we do closed curves?
It should that gamma A equals gamma B.
Is it enough to have gamma A equals gamma B?
And gamma should be continuous.
Yes. Is that enough though? What do you think? So there's two ways to do that, arguably. Okay? So let's do gamma like this. And if you want to have a closed curve, you can have it closed like this.
Yeah.
Then it's enough to say gamma A equals gamma B.
So it means it needs to always to be smooth.
It's to be smooth.
Okay, so
But how do you do to say that this point is also smooth? You know, you don't want the corner here,
okay.
right?
Yes.
You want it to be round.
So maybe you add gamma from S1 to R2. Which is a smooth mapping from. Yes.
Because S1 is a circle which is smooth everywhere.
Yes.
Okay? It is it is the only example of a manifold you need.
Yes, one manifold to the
It's the only example of a manifold you ever need, basically, because that's the reason to define a manifold.
Yes, right.
Okay?
And actually, S1, so we can only consider the case when A equals 0 and B equals 1.
Well, there are reasons not to do that.
We can think that 0 and 1 is the same. So we can
Yes.
these.
There's multiple ways to define that.
So that's smoothly.
The question is what is smooth. Okay? The question is now what means smooth. Yeah? Of course, if you see that circle, you can say, well, I have a map from the circle to R2. But whenever I have a circle, I cannot differentiate anymore.
Oh, so
I cannot differentiate because it doesn't really make sense to differentiate, right? I mean, without further definitions.
yes.
Because when you differentiate, you can only with.
So now we know what means smooth for between Rn and Rm, right?
Yes.
Okay.
So what does it mean to have smooth here?
So you mean smooth mapping?
Yeah, smooth mapping that starts on S1.
Okay.
What does it mean for that map to be smooth if we only have actually that this map is smooth, right?
I think we can define this. for all intervals in S1, we know that this is a continuous mapping to R, right?
Yes.
And so.
But that's only continuous.
Yes. We will consider the case when this is like cosine of V. Here we will only consider one 0 and 1. Or for this case, from theta and phi, things.
You can do that.
So the mapping given there is to cosine of there is an x and cosine x and sine x. And then it gives this is open, so this gives a smooth mapping from this to this. So if S1 is smooth to another symmetries.
Well, we only want R2 as a target.
Okay,
so
yes.
it's fine. I mean, just R2 is fine. S1 to R2.
So we can consider these intervals in R. So because they are R2, so for this little interval R, because so this is a mapping from maybe phi and v, okay, and this from u. Suppose then it's a one-to-one map from R to this one. So that because phi is it can be seen as R to R2. So we already know that what kind of phi is smooth. So suppose this is smooth and this is also smooth. So we say
now phi is not from R2 to R2, right? From phi is not R to R2. Here, phi is from this interval to
U. Okay.
Phi is other way around. Okay, we can do that.
And then R2. So suppose they are smooth and so there's a U theta R. So this is F. We say F is smooth. Because they are one-to-one mappings, so there is this one F theta. So this is R. In this case, then V and this, such that this diagram is yes.
Yeah. Well, two things.
So
yeah.
we say this is smooth, if and only if this is smooth.
Yeah. So you don't need to tell that, right? So it's like okay. But the question is now, why is it a notion that is independent of this here? Whatever phi you choose,
yes.
it should be independent of that. Otherwise, it would depend on phi.
Yes.
That's bad, right?
Yes.
We want a notion of smoothness between this part and this part, which is roughly right. Okay? That is independent of this. And we want to say this map, well, I mean, you don't need this one. It's just maps to R2, anything, right? Because the image will be already small. I mean, doesn't matter. So this one doesn't matter. You want something here, right? That is smooth, which doesn't depend on phi. Whatever phi you take, if for one phi the map is smooth, for every phi the map is smooth. Otherwise, it doesn't make sense, right?
Okay, so it's like this. So for instance, there are two. We only consider these parts.
Yeah.
So sorry. suppose there's a 2, 1, 1 and 2. Suppose we know that they are all smooth. And 1 to 1 and smooth.
Yes.
And then exists one and smooth. Then so.
Yes.
We know already that there exists a phi 1 theta, and because they are all smooth and 1 to 1, so there exists only one such that phi 2 these things.
What is the map between this one?
From R to R.
Yeah. What is? Give it a name, or give it how does it?
Maybe.
Write it in phi 2 and phi 1. No, it's in phi 2 and phi 1. You can write it. Right?
Phi 2 G phi 1.
Yes. So it's
Yes,
G is
because
equal
they are
to.
1 to 1.
Yes. And so G is equal to.
That exists.
Yeah.
And because they are smooth, so G is smooth also.
Yeah. So phi G is. Wait.
Yes.
Wait. Just G is basically something like phi 1, phi 2 inverse,
Yeah,
right?
that's right.
I mean that I want.
Yeah. Okay.
Okay.
Okay. So this case we will give another mapping of this. Now we will prove that then it's uniquely phi 2, because we will define the phi 2 such that this diagram alone, and this means that phi 2 equals G sec phi 1 theta, and by this one is phi 1 theta sec phi 1 sec phi 2 inverse.
Yes.
So this makes it so suppose we have 2, 1, then it's the same.
So
So
if
it
the one is
doesn't
smooth,
matter- so it doesn't
exactly.
matter by what's the mapping here.
So as long as phi 1 and phi 2 are smooth, well, if you have to, you cannot really. So if this one is an abstract manifold, then you cannot say whether phi 1 or phi 2 is smooth, right?
Yeah.
Because this thing is not necessarily in R2, it's somewhere else, right?
Yeah.
So you cannot say whether this is. But what you always can say is whether this map here is smooth, because it's only a map between R and R on Rn and Rn. And this is always given like in this form, okay, with the appropriate domains. And this thing is called transition map. So the only thing that matters in manifold is a transition map, okay? That's the one catching point. And then let me give a definition that is slightly more easier to understand. Instead of S1, one could write AB, and then you would what? Write A. And so on, depending on how smooth you want it to be. So instead of defining something on S1, we can define it on the boundary that everything needs to be the same. Not only the points, but also all its derivatives to whatever degree you want, okay? And the difference basically is the following. So this. So the difference is the following. You can consider S1 to be R mod some whatever. What do you like, Z, to have it 0, 1? Yeah, 2 pi Z. So now, what can you write? You can write, you can take a lift to 0, 2 pi, right? And now when so between 0 and 2 pi, you can always say what differentiation means, right? But at 0, you have a problem because the boundary of that interval, what you take is 0 minus epsilon, minus epsilon, and epsilon. And that as a subset here, we can say what that means. And we can take 2 pi minus epsilon and 2 pi plus epsilon. And we can say here what smooth means. Add 2 pi and add 0. Right? It's the same thing. And then you say, well, but 2 pi is equal to 0. And here we have a differentiation, and we have here a differentiation. They have to be the same point, so it must be always the same. Okay? It's multiple ways of defining this. The same thing. But my message is the following. First, if you want to do manifold, because that facilitates the way you are describing things, instead of AB, you can just take S1. Then you have to define all sorts of things. Okay, first, before you would be able to say what this means to be smooth. But then it's easier because then you don't need to specify both boundary components of your interval. Okay? So if you prefer, you just take this definition and then say gamma of A equals gamma of B, and that's not only for every differentiation, if you want it smooth. Okay? It's the same thing. Well, as a differential geometer, I prefer S1 because I'm too lazy to write this, right? But okay. Now we have defined a closed curve. Now let's see what happens. Let's define first maybe such a thing, such a map is called a parametrized curve, yeah? Okay. Okay. Parametrized curve. Because we have an explicit function that gives me the thing. Now, what are the examples of parametrized curves?
Oh, this is many. For example, a circle.
Yeah, sure.
X equals sine t, y equals cosine t.
Yes. So gamma of x is cosine x, sine x. That would give me my circle. Right, at the circle.
And I think for gamma, for the saying that the curves that I think there exists kind of polynomials or something such that it can its limit is that.
Yeah. Well, the other example are graphs. Okay, so most of the time you would take graphs. What are these? You just take f of x, some function, or ab to r, and then you take gamma to be, what is the graph of f? F of x.
This is not. This is obviously not a closed curve.
It cannot be a closed curve, yes. But this is a parametrized curve, that's no problem. So. But let me give you another example of a smooth curve, and you tell me how it looks like, okay? If t is greater than 0 equals, and e to the a minus, maybe, or minus 1. Let me. Wait a sec. I need to. I have a problem here with the 0. Wait a sec. You need maybe to repair my example here so that it becomes smooth.
But actually, this is trivial curve.
What is a trivial curve? I mean, what?
Okay.
I need a curve that is smooth.
Yeah.
So the 2 points should fit together. And I think I need to minus 1 somewhere, but it's okay. Wait, minus 1.
Okay.
And here would be minus 1. And plus 1.
Okay. I know.
So how does the curve look like?
let u example we will first consider these the front terms. Then it says t bigger than 0. So this is 0 to 1.
Yeah.
And so this is called gamma plus t is gamma minus t. Then gamma plus t equals flat and gamma.
Well, I think I have to 1 over something, but it's okay.
U equals like this u minus
Oh no.
u minus 1. So we have that like this, and then u in 0 and 1. So so the first one u minus 1 u minus 1. And
Yeah.
and because u in 1, so for example this is R2. Then it's like this. This is negative 1. Like this. And gamma minus t is similar. Gamma minus t equals this u minus 1 to u plus 1. And so u minus 1 to u plus 1. And in this case also u in 0, 1. With t and t is 0, so this case u in 0, 1, right?
I want it differently though. I would like to have the following curve with this thing. Can you?
Okay.
Other way around, okay? I'm really bad with formulas. I would like to have this curve, okay? Really similar to the example, but I want it to be smooth. Can you find me a parameterization of this curve, which obviously has a corner, okay, which is smooth?
So the corner is round.
No, it's not round. It's sharp. The corner is sharp. So the curve is really this curve, but the parameterization is smooth. Basically with what I gave you before, and I think I just had 1 over something wrong, but you can have it.
Okay.
Right? Okay.
So you want this term to be finitely length?
It doesn't matter whether it's finite length or,
So
you just restrict your...
We can define gamma t as t negative t less than 0, and 0, 0, 1 t equals 0, and t 1 t bigger than 0.
Yes, but it's not smooth, right?
Yeah.
No, it's not. I mean if it's t 0 and t minus t or t minus tt, or this way rather. The problem is if you differentiate that at 0, it's 1, 1 and 1 minus 1, so it's not smooth.
Huh? Or we can.
I mean, the example I gave was basically this one. So the idea is so basically TT, right? And probably should have done this way, because then at 0 we would have 0. And if I have negative, I would want this one. And the advantage of this thing is the derivative is always 0 at 0, 0. Yeah? So that means.
Oh, I got it. I know.
Okay.
This is a smooth. This is in the shape smooth functions, but not the one c omega. So okay.
So what you observe is the following: I have a map that maps on this image smoothly, right? At every point it's smooth, even in t equals 0, because the derivative is just 0, 0.
Yes.
It's just 0, 0.
Yes.
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 To any order. Yeah?
Yeah.
Okay?
Whoa, pretty good.
Yeah? To any order, the thing is 0. So no contradiction at all that.
Because this function e to the power of negative t squared over 1, this function is smooth in R.
Yes.
But when you consider it on C, so it 0, 0 is its kind of singularity like that.
Yes.
And
Well, it is not the analytic function. Yes.
Yes, but it's smooth.
It's smooth. Yes.
If you add 0 to it.
Yeah.
Yes.
So basically, if you take the Taylor series, it would be constantly 0, but it's not the 0 function. So now, what is the difference of this curve versus this curve?
It takes a map from t to e to the power of negative t squared over 1.
Yes, but what is the difference in this? I mean, objectively, if you look at it, you see a difference, right, between this curve and this curve. This has a corner, and this doesn't.
Yes.
So how do we prevent this from happening?
I think it's just like this. For example, you see t as the time, so the obvious the previous one is like this, but the next one is like this.
Yes, but what is how to exclude? Okay, I want to define something that excludes this from happening, because this is not smooth, right? I mean, when you observe, you look at it, it's not smooth.
Yeah.
This is kind of pathological example, because I just kind of faked it that it becomes smooth, right? So what would be the condition I need to add if I only want to consider these kind of curves? What is the main difference? What do you think? So when you look
Oh,
at
I got it.
yes,
I got it. Because, you will not only consider one curve like this, but all the maybe for open subspace of that curve, you may consider all the you may consider
it's far easier.
all the smooth ones
It's-
from the
Yes, but it's far easier. Far easier. Let me draw a picture, okay? You have this thing, okay? And you would, at every point, you would have a tangent space or tangent vector, right? If you drive a car, right? You would have a direction. Well, it's not bad. Let me just draw it like in a curve, then it's like easier to draw. The tangent vector is not completely lying on this curve, okay? Let me just do this one, okay? This one as well has a tangent vector. Let's go the other way, just do. So I drive with a car from here to here with the curve there, okay? The left-hand side is smooth. So at this point, my direction would go this way. And at this point, my direction would go this way.
Yes, it have not. This point tangent is not well defined.
It's not well defined. So basically,
You don't have a tangent.
you don't have a tangent. And if that needs to be smooth, okay? The only way it can happen that this is smooth is both vectors are 0. Well, it can only happen right? So basically what happens if you drive a car alongside your street is the following. You have to brake, you have to come to a stop, and then you change your driving wheel and go in the other direction. You cannot pass this point, okay, with positive speed. Then you're out of the street. Not good, right? So
You need to stop here. Turn your direction.
and then go, okay? The only way to do it, because you have two different directions to go, and the only way to do that. So when you have such a curve, it's not necessarily to brake, right? And to halt, and then change the direction. So the difference is what we are called regular curve, or regular curve, parameterized curve.
The derivatives are always not 0.
Exactly. So it's
That is, you cannot stop.
you don't need to stop at least. Yes. Okay. So. Again, this is really important because my gamma prime, this vector here, that gives me my tangent space, right? Gamma prime at t times r is basically my tangent space. And if that is 0, then the tangent space is just not defined. Of course, you can have this 0, but at some point it's not 0. Then it's also defined, I guess, yeah? But if you really have a corner here, every derivative must be 0, yeah? So we have now curves. And we have a parameterized curve that makes it slightly easier to consider curves. And we have what means to be regular, so we avoid the corners, right? But as we said before, the geometry should not depend on the parameterization, because I'm not only interested in the image. How to do that? The geometry of a curve like this open or close should only depend on the image of the curve and not how I go through. So basically, I have a road somewhere, I drive through the road, and no matter how fast I drive and how much I brake or how much I change my speed, the curve, the road is the same, right?
Yeah.
So how to model this fact that it doesn't depend on the parameterization? There are two ways to do it. So the one way, let me just, ooh, that was wrong. That didn't work out. So one way is by
I know. You can consider two one gamma 1 and gamma 2 from A B to R2, and consider something through their derivative.
Yes. Basically. So let me just write the first one because maybe that's something you don't think about, which is we consider something like this.
Oh, I got it. Wow.
Okay? The first way to do it is to say I restrict my speed. Then there's only one way from A to B. Right? Speed 1. Yeah? But of course, from A to B is a different curve than from B to A. Right? Then this L here is the length of the curve.
This is a question that how about the curve's length is positive infinity or like that?
You can have, then it's just R plus.
Okay.
That's fine. But if it's finite, then the thing is always the length of the curve. Or rather, gamma of t, or t is the length of the curve from 0 to gamma of t. Right? So this gives me a way to define.
This is an error. So, for example, we can consider this really so maybe because we know that arctangent function is like this. This one.
You don't take that.
Suppose is gamma equals gamma t equals tangent of t 0, and this is from 0 to negative.
What is that curve? Your gamma of t0.
It's like the infinitely long line.
Yes.
But now gamma 0 is not defined. So how to define this infinite curve? If you think that the noted definition of tangent t with at the end, then this is not a curve because. But we want to consider. We want to consider the case there.
You can there's multiple ways, right? Either you start with R.
So this needs to be R, not R plus.
Yes.
That's really not common.
So it's R, and then you would say that instead of t being the length of gamma 0, gamma t, you would say t1, t minus s is the length from gamma of s to gamma of t. So it both and at both ends defined, right? So it doesn't really matter in this case. But then what you have as a problem is integrability, right? Everything needs still to exist. Because, so this line here tells you what t is. When I give you a curve like this, how to find a map from AB to 0L so that my gamma tilde, which is has the same image, does satisfy this property. Hmm? So this property shows you how to define that.
Oh, I got.
You would what to do? What is here?
Okay. We consider a function. We will consider a function.
Aha.
AB 0L.
Oh, don't do that.
This is by gamma. And so this is by gamma theta. And we'll show that the map exists.
Yes, but how does the map look like?
For example, this is F. So we define F from AB to 0L. For speech like this, this is the for example, this is AB. AB. This is X, and this is the curve. Gamma, and then this one the gamma, gamma, prime of X. This one is not equal to 1, or because it's smooth, so it's not equal to 0. So we will let this one to be the speed of this.
So how does F look like?
So this was F. So for example, this X. Then it maps to this is just like a differential equation.
Well, it's not a differential equation. You write down exactly what F is, right? You can do it with differential equations, but this is far more explicit. What is fx?
So it's just like fx equals.
No. You can write it down explicitly what is under the integral.
Oh, I know. Suppose the length. Suppose gamma x is a function gamma a to x. So it can be length of gamma ax plus this one.
No plus, but just no plus at all. But what is length of gamma? That's a question, right? What is the length of gamma restricted to 0ax? What is it? How would you compute that?
So what is it?
What do you think? I think it's roughly that, but it's not quite. Yeah.
So oh, I got it. That is length of AX. Is that right?
Yeah, sure, but just write down the formula for length.
Okay.
What is d mu? Do you know? How would you compute the length of a curve?
Like this. But
What is d
now
mu?
we consider in R2.
But what is d
So-
mu?
So it's like this. We can. Oh, I have already. Again. 0 to x. This one, but because we know that this, so we can make it easier. Suppose gamma equals the first one is gamma 1, gamma x, gamma y.
You can think for yourself as well. Just
So-
try to find a
this is
formula.
square root of gamma gamma x t square plus gamma y equals t dt.
What is gamma x and gamma y? It's not quite true, yeah?
So suppose
So
gamma
draw a
AB
picture.
equals gamma x a gamma x b.
Sure.
No. Sorry.
Yes. What would that compute? Have you just draw a picture? And you can think about that as well. How would you compute the length of a curve?
So the curve is like this. Example, this is gamma, and the t is the time. So like this, and so given t, this is gamma x t.
Yes.
This is gamma y t.
Yes. But the length of that
And the length of that is
not
just,
really the length of the curve, right?
Yes, but the half one from
No.
a to t.
Yes, but we want this part. The question is how to compute this part.
I read it down.
No, not even half of it. I mean, this one would be length between these 2 points, right? Or rather, it's not even that is not. I mean, this is the length of. Oops. So this is my point, gamma, and what you've written down there is the length of that vector. Yeah. It is. It is gamma xt, gamma yt, so that we're computing using Pythagoras the length of this vector.
No, this formula is not.
It is. I mean, before integral, just this.
I got it. It's not. It should be the derivative of it.
Perfect. Okay.
Derivative.
You need to do the derivative first. And before you're writing this, it's better to write just the norm of gamma prime, right?
Yes.
Okay. Now, when you do that, and you take the derivative of that map, okay? We said we want something where gamma prime is never 0.
Yes.
Okay, but if you take the derivative of the map and you have the gamma prime is 0, then the map here from here to here will have a 0 derivative point,
Yes.
which is not meaning that it's not quite well defined. So when we're restricting to the regular part, we also have a good inverse. Okay?
Yes.
And that's why we need regular. And this thing is called arc length parametrization. Okay. Okay, so now you have a curve, you have basically a road there, and you drive through the thing. The question is, how do you measure whether you are on a straight line or whether you have a curve, which is curved? How do you measure that? What do you think? Yeah, wait. Let me. Yeah, how to measure that the curve is curved? Yeah. Okay. I have a straight line, or I have something like this. So how would you measure that? And then I guess it should be enough. Wait a sec. So when you have a straight line, so assume this is a road and you are sitting in a car or whatever you like to drive on this road, okay? When you have a straight line and you go by positive speed, you don't stop, okay? What happens on the straight line?
Zero.
No, the curvature should be 0, but what do you do when you're sitting in a car?
No turning.
No turning.
Rotate.
No, nothing, yeah.
And so this one, because it locally looks really like a circle, so the rotation angle is the circle's angle.
Yeah.
So
Mm-hmm.
maybe the curvature, so the curvature can be defined by the circle's radius, 1 over the circle's radius.
That's one possibility. The one possibility is to say, well, we take a circle that fit in here locally, okay? And then we take the 1 over the radius squared, maybe not, squared. Yeah? Whatever, just measures with it. What the other possibility? Oh, by the way, another thing. If I drive very fast through this, I have to turn a lot more, right? Have you ever experienced that? If you drive very, very fast through a road, then you have to turn a lot, while if you're very, very slow, you can turn a little less frequently, right? So,
Okay, so
what is the
let's
turning?
Restrict the speed. Restrict the speed to 1 and measure the turning.
Yes, but how to measure the turning?
The angle between two tangent vectors.
Mm-hmm.
Okay. I got it.
Sure.
Sorry, socks is here. Okay, and we have some tangent vector here, and let delta t approaches when delta t approaches 0, the angle delta theta over delta t.
Yes.
Okay.
You can do that. But what does it mean for the curve?
Rotation.
That's true, but can you write it more with gamma and more not with, I mean, delta t is going to 0, right?
Okay.
What does it mean?
So can I use the Gaussian map?
You can use Gauss map, but actually, when delta t goes to 0, what do you get from here? What is this? It would be theta prime, right?
Yes. Yes, obviously.
Yes. So now what is theta?
Theta should be
What is this? What is this vector?
This vector is
I can write down. What we have is gamma, right?
yes, the gamma, and Yes. Yes, and for this are two this kind of maybe A and A plus delta T. This gamma prime A and gamma prime A plus delta T. We want it into a circle.
Yes.
So divide that by gamma prime A. Divide by gamma prime A plus delta T. So the angle here is theta A.
Yes.
Theta delta PA and theta A is defined by limit when the T to 0 theta delta PA. Okay?
Sure, but put it into proper formula. What is the proper formula for this thing? Now in terms of gamma. You can write the theta down in terms of gamma. Just with gamma.
Yeah.
Right? You don't need theta. It's there. And assume it. We had already said we restrict to arc length parameterized curve. So these are all ones, right?
Yeah.
Now write down what gamma prime now is. What is gamma prime?
Gamma prime.
In terms of theta. If it's arc half length 1. What is the theta?
Gamma prime equals
Well, it's maybe not cosine but sine, but it's okay.
Yeah.
Right?
Yeah. But
And what you have here is theta prime.
Yeah. But you need to the gamma should be like that. I think. It should be.
Yeah, it's arc length. It's arc length.
Yes.
It's 1.
Yeah.
So this is 1.
Yeah.
So that we would do first, right? We will restrict to something that has unit speed. So that's 1. So this maps to S1. It looks like this. And we want theta prime. So how to get from here theta prime? So this is theta t, right?
So what's the derivative of our cosine? It's cosine. What is cosine?
So if gamma t is already given, okay?
Yeah.
How to compute the curvature just from gamma t?
Okay, I got it. But I think it only depends on gamma xt because gamma.
Yeah, of course, but it can do that. But it's not. I mean, geometrically, it would make sense not to distinguish between gamma x and gamma y.
Because this is like this. So cosine of theta t equals gamma xt.
Prime, yes.
And so theta t equals arc sine of gamma x prime t.
You can do that if you want to.
Sine. This one is 0, so okay. So theta prime t equals arc sine gamma x prime t prime equals gamma x 2 t negative. So this is negative. Is that?
What is this here? The second derivative?
Yes.
Okay, you can do it that way. So basically what it says is that the curvature is related to the second derivative. But let me write it in a more easier way, which is if I just take the second derivative, I would have that is theta prime, and then I would have minus sine theta cosine theta, right? But what is this vector? This is just orthogonal.
Oh, yes.
So this is a normal vector.
Yes, I know.
Normal.
I know.
So instead of computing this very complicated thing, you can just take the second derivative of gamma and take this scalar product with a normal vector, and it gives you the curvature. And it's called kappa. Okay? So, and that holds whenever you have an arc length parametrized curve. You have to first restrict your speed. So the question to think about till next time is first, what is the formula for kappa for non-arc length curves? And second, what is a discrete curve? And what is the curvature? Okay. We're done for today. Thank you so much. We see each other next week. And if you have questions, just ask me now.